Welcome back. Let's talk about monitoring. In this section, we are going to take a look at monitoring MySQL via the database itself with command line utilities, and last but not least, monitoring MySQL with external tools. First, let's talk about monitoring via command line or manual monitoring. In this video, we are going to look at monitoring MySQL via the database itself and bundled tools. We will also discuss some useful command line utilities. We saw earlier in a detour that MySQL maintains status counters. They can be checked via show status or show global status command. The MySQL admin bundled client program has a mode where it issues show global status periodically. In the example on this slide, this invokes show global status every second. The output alone is not too usable because there were just too many variables and some of them are wide as well. The number of currently running threads every second, on the other hand, is very usable. Threads running is a very reliable metric to tell if the database is overloaded or not. It shows all the connections that are doing something at any given time. This approach won't work well for some other commands though. For example, the com_select is a counter which will be ever increasing. Because this is a counter, it is very hard to follow, especially on busy servers. Here, checking the per second difference would be more useful. Luckily, there is a utility for that in Percona toolkit. pt_next is for formatting MySQL admin output. We will see how it works in the lab at the end of this video. The show process list is another essential command for monitoring. It shows what each of the client connections are doing. The performance schema is also a great source of monitoring information. It provides low-level instrumentation for the server at runtime. The running MySQL server can be examined with it, in other words. The sys_schema is a layer of stored programs like views, procedures, and functions for performance schema. It provides a nicer user interface and it's much easier to use. The sys_schema is bundled with MySQL 8 by default. You don't have to install it separately. For example, it's useful for getting the top queries of the server. This can be done with examining the sys.statement analysis table. The $$ tables in the sys_schema are unformatted ones. For example, the total latency column in the previous table is text with formatted human-readable values. In the $$ table, we see the raw values, so it's more flexible to use with more complex operations in SQL or with readings with machines, not by humans. MySQL also has the slow query logs for ages. Percona server has a significantly enhanced version of them. By default, the slow log is off. The first statement on the slide will turn it on. The second statement tells MySQL to log every query which lasts greater than 0 seconds, so basically every query. Basing decisions on only slow queries, let's say which are slower than 1 or 2 seconds, might skew the picture, because a query that runs 10,000 or 100,000 times and each takes 100 milliseconds is a more viable optimization candidate than one that runs twice and each takes 3 seconds. With fast slow logs, MySQL closes the file descriptor for the slow log and will open it again. If this is the first time the slow logs are turned on, it will create the file. This is how a slow log of a single event looks like in MySQL 8. You can see the query at the bottom and the metadata of the query on the top. The query is select1, so it's only the last row. PT_query digest from Percona toolkit is a very flexible slow log aggregator. For several years, this was the de facto tool to determine what the top queries are in a MySQL instance, and it still works really great. The show engine InnoDB status command provides InnoDB specific monitoring information. Luckily, more and more of these are available via normal status counters and performance schema in a format that can be more easily processed. I could talk about InnoDB internals and interpreting show engine InnoDB status for several hours, but let's leave it at this for this course, that InnoDB specific information can be gathered with this command. We already used show slave status command for monitoring replication. Apart from that, for more complicated replication setups like multi-source or group replication, there are tables in performance schema as well. pt_heartbeat from Percona toolkit is monitoring replication by writing a timestamp to a table periodically, which can be queried on the slave. This is useful if the IO thread is the bottleneck. In that case, seconds behind master from show slave status will fluctuate. The reason for that is that seconds behind master is calculated using the current timestamp and the timestamps in the relay log. If there are no relay logs, it displays 0, but the reason for no relay log can be a slow IO thread. Monitoring the basic metrics at the operating system level like CPU, memory, IO, or disk space still makes sense for database servers too. Running out of disk space is a very common reason for database outages. The PT Stalk tool from Percona Toolkit collects very granular monitoring data, but only after a trigger condition is met. By default, this trigger condition is threads running reaching a certain threshold for a certain number of seconds, which is a very good indicator of MySQL being overloaded. It very rarely needs to be changed, but we will change it in the lab, just so we see how to do that. Let's do Lab 5a together, where we will examine all these tools. Hello and welcome to the lab where we will try manual monitoring. First, let's check our environment. I have 3 terminals prepared because in this lab we will use 3 machines. 2 of them will be a master-slave database pair and 1 of them will be a sysbench machine running sysbench to put some load on our databases. Let's start this environment up. It's up. Thanks to video editing, this was very fast for me, but it won't necessarily be this fast for you. So let's log in to the sysbench node, the master and the slave. So I'm gonna use the upper terminal for the sysbench. I'm gonna use the middle one for the master. And I'm gonna use the bottom one for the slave. So we logged in to all of them. On the sysbench, we will run the prepare command to create a database where we will run the workload against. So I'm just copy pasting this command right here, and it is creating a database. It's done. So on the sysbench node, we will run some workload against the master. This has a rate limit of 10 transactions a second, so this is a very light load. We will do the rest of the labs while this light load is running. First, let's check the basics, like how to check IO, CPU, and things like that. So even for the database server, you can check the IO utilization with IOstat. This isn't really MySQL specific. We can see that there is a bit of an IO going on, especially writes, as part of these transactions, but nothing too serious. We can also check the CPU utilization with mpstat. Which is again very light. It's using around 1–2% of CPU. Let's try running MySQL admin x-i for a few seconds. Remember that this is gonna print out all MySQL status variables. So this output is like not really usable. we can grep for a certain variable. For example, if we are curious about the select volume caused by this workload, we can just search for comSelect, but this isn't really helpful because comSelect is a counter which increases at every select. We want more per second values. So we can use ptmaxed. For ptmaxed, we are going to supply MySQL admin x-i1, and we are going to supply 4 samples. The C1 means run it 4 times with a 1 second delay. So ptmaxed will parse the output of this MySQL admin and will create the max.out file. This will take 4 seconds because it needs to gather the samples. So let's check the contents of max.out. So here what we see is in the first column for each variable, we see the global value, and then in the next 2 columns we are seeing the per second changes. If we search for comSelect here, we could get the global counter and then the per second of the number of select operations that we hit in the 2 different seconds that we are taking the sample of. We can see that the workload is fluctuating, like here it does 6 transactions per second, here it does 11, so it makes sense that we are seeing this amount of selects. One of the transactions has more than 10 read queries in it. Okay, on the DB1 we will start ptstalk, so in a way that we are watching the threads running variable, we will trigger a data collection if the threshold, if threads running is more than 5 for 2 seconds. So let us start ptstalk. And by default, ptstalk will just do nothing. It will watch for the trigger event, but the database server is not really loaded. And of course it's not really loaded because this is a rate limited workload, and even though if it wasn't rate limited, it uses 4 threads. So it's pretty much almost impossible to have threads running at 5 if we have 4 client threads in total. So let's use Sysbench to put some harder workload on this database. Here we will have the threads running at 40, and it's the number of client threads at 40, and it's not rate limited. So this will trigger the ptstalk almost immediately. We will stop Sysbench as soon as it triggered the ptstalk because this is like a very heavy workload. So let me cancel this, start the new one. And here we can see it matches immediately. We had 2 samples where it matched. So let's kill Sysbench here. And we are killing ptstalk as well. Pressing Ctrl+C, it will finish the data collection. It is up to 90 seconds until all the sub-process is finished. It's a very good idea to run ptstalk in production continuously, because if there is an overloading event which needs to be examined, we would have some data. So in next step, we are going to examine the /var/lib/ptstalk directory where the collected data is. So ptstalk exited. Let's go to var/lib ptstalk. And here we have a lot of captured metrics via the command line tools, like what we would do as we run these commands. For example, we have the output of mpstat. How was the CPU? We have the output of iostat, let's say. Right, how was the I/O? It's somewhat heavier than what we saw earlier. Also, we have the full MySQL admin output. For example, we can get the threads running from this. So we know what was the threads running operation during, what was the threads running variables value during this data collection. We also have the process list captured, like show process list every second, and a bunch of other things. Like this is really rich monitoring or troubleshooting information, source of troubleshooting information. PT's talk has a pretty good documentation. Going through all this would take a lot of time, probably another course like this. Okay, on Lab 5e DB1, let's start a MySQL client. And now we will learn to use sysschema to get the top queries. So first, we will take a look at sys.statement analysis. And this is the well-formatted output. For example, what we see here is total latency is a text column because it has human-readable output. We can check the $$ statement analysis table. We can see that this is the raw value because things like total latency is a big int. It's in nanoseconds. So we can examine, for example, the top 3 queries by latency. Here they are. It's from performance schema. This is not really readable like this because it's in microseconds. The other is show global status because it ran a lot of time, right? Because we ran MySQL admin quite a few times. And we spent the most time in begin, and it was executed during our lab more than 5,000 times. For example, if we want to examine the top queries by rows read, we just rows examined, we just have to order by rows examined. What I expect is that begin won't be there, and there would be more performance schema queries. So yeah, exactly. This is getting table metadata. So rows examined is 3000. This is again a performance schema query. Rows examined is more than 11,000. Checking variable by threads. And show global status actually examined the most rows in our workload now. Begin doesn't appear here because although we spent a lot of time in begin, it didn't really examine any rows by itself. So let's exit from the MySQL client on the master. And now we will use the slave. We are gonna start monitoring replication lag like this, just executing show slave status, grabbing for seconds behind master and do this every second. So this is like poor man's way of monitoring slave lag. And we start a workload on lab 5a db1. This workload is not rate limited and it is not using the normal OLTP Lua from sysbench, it is using OLTP update index. This workload does lots of very small writes. If this is parallel enough, it will trigger replication lag. So we can see that replication is caught up because we don't have any traffic on the master. That's expected. But as soon as I start the workload, the replication lag is start to crawl up. Because on the master I'm updating on 16 threads, updating random records on 16 threads, and on the slave it is processing the update only on a single thread. I stopped the workload on the master, but we still see the replication lag growing because we just put in 14 seconds worth of workload on 16 threads, and now what we see is that the slave thread processes it. And after 26 seconds it dropped to 0, so it processed the relay log fully. So it took 26 seconds on the slave side to process 14 seconds worth of massively parallel or have more heavily parallel writes. Not massively because, these are just virtual machines on a lab, but a more parallel writes was processed more slowly on the slave. So we have seen replication caught up. So the only thing left is exit from everywhere and destroy the environment. We are done with the lab about manual monitoring, let's say.